Hello, and welcome to this presentation on the normal distribution. This work does assume you have an awareness of the topics of data presentation, central tendencies, including the mean and the standard deviation, and also basic probability. An overview of the normal distribution. Within statistics, the normal distribution is an important pattern found in naturally occurring phenomena such as weights of people, heights of trees, blood pressure readings, diameters of ball bearing measured from a production line, results in a psychometric test, errors in measurement, etc. When such data are gathered, they often form the normal distribution, which when plotted on a histogram forms a bell-shaped pattern that's symmetrical about the mean, the x-bar value. In this diagram, here's the mean, the x-bar value in the middle, and we've got a symmetrical bell shape about the mean. This relates to the shape of a normal distribution, frequency plotted on the vertical axis and the variable on the horizontal. The total spread of the normal distribution curve is actually plus or minus 4 standard deviations, the symbol sigma being used for standard deviation. And that's from the mean. But as only 0.13% probability occurs in that 4 standard deviation, often the range of the curve is described simply by plus or minus 3 standard deviations, which accounts for 99.74% of the population. So on this diagram here we can see again the bell shape about the mean, the x-bar value, and if we add up the percentages we essentially get nearly 100% under the plus or minus 3 standard deviations. So here's our mean, and to the left of the mean we've got 1, 2, 3 standard deviations, to the right of the mean 1, 2, 3 standard deviations, so plus or minus 3 standard deviations from the mean shown. Thus, if our data collected follows a normal distribution curve, we would expect it to lie within plus or minus 3 standard deviations of the mean. The normal distribution is one of the most important probability distributions and is applied directly to many practical problems in engineering, such as assessing the reliability of mechanical devices and the ability of items that are manufactured on a production line to meet the required specifications. Within medical pandemics, for example the COVID-19 outbreak, the normal distribution can be used to help model the rise, peak and decline of expected cases based on various assumptions made. These are shown in the diagrams below. Okay, normal distribution, introduction here. When data is obtained, it's frequently considered to be a sample, that is a few members drawn at random from a larger population, for example ball bearings. If the sample number is large, say 100 components taken from our production run, the results will generally follow the normal distribution profile. The normal distribution is shown in figure 1 and it's symmetrical about the mean, as we've already discussed. The curve is described by a mathematical equation, and this is the basis of much work done in advanced statistics. Standard deviations. Figure 2 shows the area of a vertical strip of 1 standard deviation, symbol sigma, as a percentage of the total area under the curve. So in the first standard deviation to the left and right of the mean, we've got 34% of our population on either side. In the second standard deviation on either side of the mean, we've got 14% of the population. In the third standard deviation either side of the mean, we've got roughly 2% of the population. These areas can be used to estimate the chances or probability of an occurrence which is very useful in quality control. For example, there is a 34% probability of an occurrence between the mean value and one standard deviation from the mean. In other words, here's the mean of our standard deviation curve, and one standard deviation to the left or the right is 34% of our population, or 34% probability an item will fall in that standard deviation. Normal distribution curves can differ in four main ways. Firstly, they can have different mean values. Secondly, they can have different values of the standard deviation. Thirdly, the variables can have different values and different units. And finally, they can have different areas between the curve and the horizontal axis. Standardization of the normal distribution curve. The following procedure is used to what's called standardize the normal distribution curve, and that's the way we will use the curve in the examples that follow. So step 1. The mean value of the unstandardized curve is made to be the origin, thus making the mean value, which is x bar, 0. Step 2. The horizontal axis is going to be scaled in terms of standard deviations. This is achieved by letting z equals to x minus x bar over sigma, where z is the normal standard variate. We'll look at this in a moment in the examples. X is the value of the variable we're considering, and x bar is the mean of the distribution that we've calculated. Step 3, we're going to let the area between the normal distribution curve and the horizontal axis equal to unity, have a value of 1. When the normal distribution curve is standardized, the normal curve is termed the standardized normal curve, or the normal probability curve. This is shown here. Again, we've got our bell shape of our normal distribution curve. Our x bar is the middle of the curve, but that's at 0 variate. The z value is 0 here. And then to the left of the x bar, we've got minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations. To the right of x bar, we've got plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. The area under the standardized normal distribution curve is equal to unity. So what we will be doing in the examples that follow is to use the standardized curve, looking for areas either to the left, to the right, or on both sides of the x bar, and using that as our probability. So the area under part of the normal probability curve is directly proportional to the probability, and the value of the shaded area shown in figure 3 on the previous slide determined by evaluating the integral shown in figure 4. However, to prevent repeatedly evaluating values using this integral, we use tables of partial areas under the standardized normal curve, and they're shown in table 1 on the next slide. Table 1 here shows the partial areas under the standardized normal curve from 0 variate to some value of z variate. Don't forget the 0 variate relates to the middle of the curve, the x bar value, and then we have a plus or minus variate, z variate, depending on our values given, so the z can be to the right or to the left of the x bar. And as mentioned previously, the z variate is calculated by x, take away x bar over the standard deviation. On the table we have the z variate in the left hand column, which relates to particular values of standard deviation. Here is the first standard deviation, second standard deviation, third standard deviation. We actually go up to 3.99 for our final value of the standard deviation. Notice it ends at 0.5 because that's the 4 standard deviations to the right, and of course there are 4 standard deviations to the left of the mean, so in total the 0.5 plus the 0.5 will give us a probability of 1. So the area under the curve is 1. We use this table for plus or minus Z values. Example 1. The mean weight of 1200 castings is given as 3.4 kilograms and the standard deviation is 180 grams. Assuming the weights are normally distributed, determine A, the number of castings likely to have weights between 3.04 kilograms and 3.86 kilograms. And part B, the number of castings to have weights greater than 3.93 kilograms. So for part A, taking information from the question, the X bar, the mean of the castings, is 3.4 kilograms, and the standard deviation, converting the 180 grams to kilograms, is 0.18 kilograms. So part 1 here. We're going to consider a weight of X equals to 3.04 kilograms. So to find the variate, the formula is X, take away the X bar, over the standard deviation. In this case, the X value we're given is the 3.04 kilograms. The X bar given in the question is 3.4, and the standard deviation in the question is 0.18. Doing the arithmetic on that, we end up with a negative standard deviation minus 2. So from table 1 on our previous page, we can work out the partial areas beneath that standardized curve. So for a Z value of minus 2, we get 0.4772. If I go back to the table, for a Z value of 2, which is here, 2.0, we get 0.4772. The negative Z simply means it's on the left-hand side of the X bar value. So a negative 2 for our Z value is the negative 2 standard deviation line here. So the area I just read from the table is this area here, the shaded area shown on our diagram. Example 1 continued here, this is part 2. Now consider a weight of X equals to 3.86 kilograms. So Z, in this case, the variate will be X take away X bar upon sigma. So now the X is 3.86, take away the X bar, which is 3.4 from the question, divided by the standard deviation of 0.18 in the question. Doing the arithmetic on that, we now find we get a positive value of standard deviations. It's actually 2.5 recurring. If we now look at the table for the value of 2.56 as a variate, we will get the area of 0.4948. Again, if I go and look for 2.56, here's 2.5, and I go along to the 6th column here, which is this one here, we can read 0.4948. So the area from the mean value at 2.56 standard deviations to the right now on the positive side gives us this partial area from the table. Again, the shaded region under the curve. Example 1 continued, part 3 here. We're going to now find the total shaded region to the left and the right of our mean value. So to the left, the minus 2 standard deviations, the area was 0.4772. So at the minus 2 standard deviation, the value, this area here, under our curve to the left of the X bar value relates to the 0.4772. And then to the right, the 2.56 Z value, standard deviation value, relates to this part of the diagram, and that area was 0.4948. Adding them together, we get total area of 0.9720. So that's the probability. So Step 4, we're going to look at the probability calculation now. Now the calculated area under the curve is directly proportional to the probability. Don't forget the total area under the standardized curve equates to unity, 1. So in other words, the probability of one casting having a weight between 3.04 kilograms and 3.86 kilograms is given by the area under the curve. That's the probability now of 0.9720. In other words, a 97.2% chance that there will be a casting between the range of 3.04 kilograms and 3.86 kilograms. So if we had 1200 castings in our batch, the expected number of castings with weights between the 3.04 and 3.86 kilogram range would be simply 1200 times the 0.9720. So that gives about 1166 castings would be expected to lie in that range. Example 1 continued here. This is part B. We know from the question that the mean mass of our 1200 castings was 3.4 kilograms and the standard deviation of the castings was 0.18 kilograms. So step 1 here, we're going to consider the x of 3.93 kilograms. This part of the question wants us to find how many castings would have masses greater than the 3.93 kilograms. So we need to work out the variate associated with the 3.93. So to calculate the variate, it's always x take away x bar upon the standard deviation. So in this case, the x is 3.93, take away the 3.4 for the x bar, divided by 0.18 for the standard deviation. Evaluating that, we get 2.944 as a z value of 2.944 standard deviations. From our table on the previous page of partial areas beneath the standardized normal curve, for a z of 2.94, we find the area is 0.4984. So that's the area between the variate z equals 0, which is at the x bar position, and the z is equal to 2.94. Don't forget, positive z's are on the right hand side of the diagram. So the area of 0.4984 is the shaded area of our bell shape here. If we now refer to our table, we can see where the 0.4984 has been extracted from. So here's our table again. Here's 2.9. There's the 4, so 2.94 would give us the area of 0.4984. Example 1, part B continued. This is step 2. We're now going to calculate the area to the right of the 2.94 variate. In other words, this little bit of area up here. We know that the total area under a standardized normal curve is unity, 1. And we know it's a symmetrical curve about the z0 value or the x bar value here. So therefore the area to the right of the z0 value is 0.5, just as the area to the left is 0.5. So to work out the tail area on the right hand side, we simply take the 0.4984, which we got from the previous slide, from 0.5. So that gives us a value of 0.0016. So that value is this area up here. So what we've done basically here is take this area, which on the diagram is this area in this part of the diagram here. So all of that area, we've taken all of that area from 0.5 to give us a little bit of area to the right hand side, which is 0.0016. Now we can do step 3, which is the probability calculation. The probability that a casting's weight will be greater than 3.93 kilograms is the 0.0016 value, or 0.16%. If we have 1200 castings, then the expected number of castings with weights greater than 3.93 kilograms is simply 1200 times 0.0016, it gives a value of 1.92. So we would say roughly 2 castings are likely to be greater than 3.93 kilograms out of the 1200 in our batch. Exercise 1, it requires us to use table 1 to find the areas under the normal curve given in part A. Got to find the area under the curve between z is equal to 0, this point here, and z is equal to 2.7, this point up here. So from table 1 of partial areas on the previous slide, we find for a z value of 2.7, the area is 0.4965. We go and check that on our previous table. So for 2.7, here is 2.7, our value is 0.4965, reading directly from the table. So what we've got here is the area, the shaded area shown here, between the z is equal to 0 and z is equal to 2.7. It's on the right hand side because it's a positive z value. Exercise 1, this is part B. We're asked to find the area under our normal curve between z is equal to minus 1.57 and z is equal to 0. And don't forget z is equal to 0 is here at the x bar position, the center of our bell, and the minus 1.57 means it's going to be a value here to the left of the z is equal to 0 position. So a negative z is to the left of our x bar line here. So for a z value of minus 1.57, the area found on table 1 on a previous slide is 0.4418. We can check that with the table on the previous slide. Here's the z column, here's 1.5, and go along to find the 7, so 1.57 gives us an area of 0.4418. Notice the table only has positive z's, but because of the symmetry, we can use this for negative 1.57. So the area we've calculated from the table is this shaded area here. That's the 0.4418 area. Okay, exercise 1, part C. We're asked to find the area under the normal curve between z is equal to minus 3.09 and z is equal to minus 0.9. So on our bell-shaped diagram here, don't forget the z is equal to 0 is here. So z is equal to minus 0.9 will be somewhere there, and z is equal to minus 3.09 is then in this region here. So for a z value equals to minus 3.09, the area from our table 1 is 0.4990. I can check that on the table for minus 3.09, so here is minus effectively 3.0, and the 9 up here gives us a value of 0.4990, that's what we read there. And then for a z value of minus 0.9, the area is 0.3159. Again, we can check that on our table. For minus 0.9 here, 0.90, it's 3159. To find the shaded area between these two z values, we simply take one from the other. So in this case, we take the 0.3159 from the 0.4990 and gives us a value of 0.1841. And that's the area of this shaded region here between the two z values. Exercise 1, part D. We're asked to determine the area under the normal curve between z is equal to minus 2.5 and z is equal to plus 2.8. So again, there's our z is equal to 0. So minus 2.5 would be down in this region, and then plus 2.8 would be somewhere up in this region. We want the area between them, so this time we're going to add the two z areas together. So for a z value equals to minus 2.5, the area is going to be 0.4938 from our table 1. If we check that on table 1, for the minus 2.5, there's 2.5 and 0 is 0.4938. For a Z value of positive 2.8, the area is going to be 0.4974 from the table 1. We can again check that from our table. Now we're looking for 2.8 now, so there's 2.8 and we can see the 4971 area. In this case we want to find the total area between the minus 2.5Z and the plus 2.8Z, so we're going to add the above two areas together to give us our total area, which in this case is 0.9912. So what we've got there is the total area between those two Z values, so the total shaded area here. Exercise 2, this is part A of exercise 2. The mean height of 900 people is 1.71 meters and the standard deviation is 0.107 meters. Assuming that the heights are normally distributed, we've got to find the number of people likely to have heights less than 1.65 meters. So from the question, our x bar, our mean value, is 1.71 meters and our standard deviation, our sigma, is 0.107 meters. So for part A, the first step is to consider the height of 1.65 meters. That's our x value in this case. So to find the variate, the z value, that's x, take away x bar over the standard deviation. So in this case it's 1.65, take away the 1.71, which is the x bar value, over the 0.107, which is the standard deviation. That gives us a z value of minus 0.56. If we look at table 1 of the partial areas under the normal distribution curve, the area for a z value of minus 0.56 is 0.2123. We can check that from our table. So 0.56 is 0.5 and 6 is up here, so we can see we got the 0.2123 area. Again, the negative z value means it's on the left hand side of the diagram, so we're talking in this region here. Exercise 2 is part A, step 2 here. So we've got to calculate the area to the left of this variate. We're interested in the people whose heights are less than the 1.65 meters. So we're interested in the shaded area to the left of our variate of minus 0.56. Don't forget the total area under a standardized normal distribution curve is 1. So the area for half of the curve is 0.5. So the area to the left of the minus 0.56 z is going to be 0.5, take away the 0.2123 area we found on the previous slide. And that gives us a value of 0.2877. So step 3 is the probability calculation. We now need to calculate the number of people in our batch of 900 that will have heights less than the 1.65 meters. Well, we know from step 2 what the probability is going to be is 0.2877. So multiplying the 900, the number of people in our batch, times by the probability will give us 259 people. So assuming our data follows the normal distribution, there are 900 people in this sample, 259 would be expected to have heights of less than 1.65 meters. Okay, exercise 2, this is part B. So again, we know that the mean height of our 900 people in our sample is 1.71 meters and our standard deviation is 0.107 meters. Again, we're going to assume that the heights are normally distributed. We've got to determine the number of people likely to have heights of more than 1.996 meters. So from the question, the x bar is 1.71 meters and the sigma, the standard deviation, is 0.107 meters. So step 1 of part B, we're looking at an x value of 1.996 meters. So to work out the variate, that's x take away the x bar over the standard deviation. So in this case, that's 1.996 for the x, take away the 1.71 for the x bar over the standard deviation of 0.107. That gives us a variate of 2.67. So from table 1 on our previous page, the z of 2.67 has an area associated with it of 0.4962. We check that on our table. And so from our table of partial areas, there's our Z column, our variate column, there's 2.6 and there's 7, so that gives us an area of 0.4962. Exercise 2, part B continued. This is step 2. So what we need to do is work out the area to the right of our variate this time, because we are looking for heights greater than 1.996 meters. So a variate of 2.67 is up here, and what we've done so far is worked out the area from our table for this part of the normal distribution curve. But we're looking for heights above the 1.996 meters. So we want to find what's called the tail area, the area up here. So again, noting that the total area under a normal distribution curve is 1 when it's normalized. A symmetrical curve, so that means half of the area is 0.5. So from Z0 to the forced standard deviation on the right hand side would be 0.5 area. So to find the tail area, which is to the right of Z of 2.67, that will be 0.5 take away the 0.4962 to give a tail area of 0.0038. So the area that we're looking for is up here in the tail. Step 3, our probability calculation. We now need to find how many people would we expect to have heights greater than the 1.996 meters in our sample. We know the probability P from step 2 is 0.0038. So for our sample, our group size of 900, multiplying 900 by the probability of 0.0038 gives us 3 people. So we would expect 3 people of our 900 sample to have heights greater than 1.996 meters. Exercise 3. A batch of 3,000 cola bottles is filled in a bottling plant and has an average content of 753 milliliters, and a standard deviation of the contents is 1.8 milliliters. Assuming that the volumes of the contents are normally distributed, we've got to find the following. A, the number of bottles estimated to contain less than 750 milliliters. B, the number of bottles estimated to contain between 751 and 754 milliliters. C, the number of bottles likely to contain more than 757 milliliters. And part D, the number of bottles likely to contain between 750 and 751 milliliters. We'll look at these solutions on the following slides. Exercise 3 continued here. I've just extracted the mean and standard deviation values from the question. The X bar, the mean, is 753 milliliters, that's the mean contents of a bottle, and the standard deviation of the contents is 1.8 milliliters. Part A of the question, we've got to estimate the number of bottles that contain less than 750 milliliters. So, step 1 here, we know X is 750 milliliters, we can calculate our variate Z. Always from the formula X, take away X bar, divided by the standard deviation. X in this case is 750, take away the X bar, 753, all divided by 1.8. That gives a variate of minus 1.67. Don't forget a negative variate meets on the left hand side. So there's our zero variate, this in this case will be minus 1.67. And from our table of partial areas, for a Z value of minus 1.67, the area is 0.4525. You can check that from the previous table. From our table of partial areas, our Z variate here, 1.67, gives us a value of area of 0.525. So from our table, we've worked out the area between Z is equal to 0 and Z is equal to minus 1.67. So this shaded area here is the area now we've worked out from our table. Exercise 3, part B. We're now asked to estimate the number of bottles to contain between 751 and 754 millilitres. So step 1 here, given our x of 751. To calculate the variate, z is x take away x bar upon sigma. In this case, the x is 751, take away the x bar 753, divided by 1.8 for the sigma. That gives us a variate of minus 1.11. Don't forget the negative variates on the left-hand side of the z equals 0. Exercise 3, part A continued here, step 2. We need to calculate the area to the left of our variate, our minus 1.67 variate, because we are trying to find bottles containing less than 71 millilitres. We know the total area under the curve is 1, and due to symmetry of the curve, half the area on either side of the x bar is 0.5. To define the area to the left of the minus 1.67 variate, we take the 0.4525 from 0.5 to leave us what's called the tail area. So the 0.0475 in this case is the shaded area here, the tail area to the left of our minus 1.67 variate. Step 3 is our probability calculation. So for a batch of 3,000 bottles, the expected number of bottles containing less than 71 millilitres is related to the probability of 0.0475 from step 2. So 3,000 bottles times the probability of 0.0475 gives us 142.5, say 143 bottles. So from our batch of 3,000 bottles, the number of bottles containing less than 71 millilitres would be 143, assuming the batch follows the normal distribution. Exercise 3, part B. We're now asked to estimate the number of bottles to contain between 751 and 754 millilitres. So step 1 here, given our x of 751. To calculate the variate, z is x take away x bar upon sigma. In this case, the x is 751, take away the x bar 753, divided by 1.8 for the sigma. That gives us a variate of minus 1.11. Don't forget the negative variates on the left-hand side of the z equals 0. So from our table of partial areas on a previous slide, for z is minus 1.11, the area is 0.3665. You can check that from our table. For 1.11, there's 1.11 in our variate column there, gives us an area of 0.3665. So we now know the area between the z is equal to 0 and the z is equal to minus 1.11, which is the shaded area on our diagram. Exercise 3 continued here. This is part B and step 2. We're now given an x value of 754 millilitres. We've got to find the z variate associated with that. So z is equal to the x take away the x bar, the mean, over the sigma, the standard deviation. In this case, it's 754 for the x, take away 753 for the mean, divided by the 1.8 for the standard deviation. That gives us a z value, z variate of 0.56. That's positives, so that's on the right hand side of the diagram, to the right of the z is equal to 0 value. From our table of partial areas, we find the area associated with a z of 0.56 is 0.2123. We can check that from our table. So for 0.56, the sixth column here, we read an area of 0.2123. Don't forget, positive z's are always on the right hand side, so the area of 0.2123 relates to this strip here between the z is equal to 0 and z is equal to 0.56. Exercise 3, part B continued, step 3. Now the total area to the left and the right hand side of the x bar, or the variate z equals to 0, is simply adding up the two previous areas from steps 1 and 2. So total area is 0.3665 plus 0.2123. So our total area is 0.5788, and that relates to the shaded area on our diagram, the area here to the left of the x bar value and the area to the right of the x bar value. Step 4 is our probability calculation. We need to find for our batch the number of bottles that contain between 751 and 754 millilitres, in other words the shaded area of a diagram. If we have 3,000 bottles in our batch, multiply it by the probability from step 3 of 0.5788 gives us 1,736 bottles. Exercise 3 continued. I just repeated the x bar value and the standard deviation value from the previous slides. So part C. We now need to estimate the number of bottles likely to contain greater than 757 millilitres. So step 1, our x is 757 millilitres. To work out the variate z value, that's x take away x bar upon sigma. In this case 757 is the x, take away the 753 for the x bar, or divided by 1.8 for the sigma. That gives us a variate, a positive variate of 2.22. That means we're on the right hand side of our x bar value. From our table of partial areas, for a z value of 2.22, the area is 0.4868. We can check that from our table. For a z value of 2.22, here is 2.2 in our z column, here is 2 in our header column. That gives us an area of 0.4868. So the area we've calculated here is the area between the z is equal to 0, our x bar position, and the z of 2.22, shaded area in other words. Exercise 3, part C continued here. Step 2. We've now got to calculate the area to the right of our variate, to the right of the z equals to 2.22 value. We're trying to find this area up here basically. Knowing that half the curve is equal to a 0.5 area, to find the tail area, it's 0.5 take away the 0.4868 we've got from step 1. That gives us a tail area of 0.0132. It's a probability. So step 3, the probability calculation here, for a batch of 3,000 bottles, the number of bottles containing greater than 757 millilitres would be 3,000 times our probability of 0.0132, so 40 bottles. So from a batch of 3,000 bottles, we would expect 40 of them to have contents greater than 757 millilitres, assuming the batch is normally distributed. Exercise 3 continued here, part D. We're asked to estimate the number of bottles that contain between 750 and 751 millilitres. So step 1, our x is 750 millilitres. To find the z, that's x take away x bar upon sigma. So in this case that's 750 take away 753 divided by 1.8. That gives us a variate z of minus 1.67. So that's to the left of our x bar value. So that's down here. From our table of partial areas, for a z value of minus 1.67, the area is 0.4525. We can check that from our table. Here's our table of partial areas. For a z value of minus 1.67, here's z, minus 1.6 there, go along to the 7 column here. That will give us an area of 0.4525. So the area we've worked out is this shaded area to the left of the x bar value. Exercise 3, part D continued here. Step 2. We've now got an x value of 751 millilitres from the question. To find the corresponding z value, x take away x bar upon sigma, in this case it's 751 take away 753 upon the 1.8. That gives us a z value of minus 1.11. We're on the left hand side now of our diagram. From our table of partial areas on the previous slide, for a z of minus 1.11, the area is 0.3665. You can check that from our table of partial areas. For a z value of minus 1.11, there's 1.1, and there's one column, so that will give us an area of 0.3665. So the area we've calculated now is the area here, the shaded area to the left of the x bar, or the z equals 0 value. Okay, exercise 3, part D continued, step 3. We've now got to calculate the area between the z value of minus 1.67 and the z value of minus 1.11, because we're trying to find the number of bottles between 750 and 751 milliliters, and they're both on the left hand side of the diagram. So the total area we're looking for here is a 0.4525, the area associated with the z of minus 1.67, and we're taking away from that the area 0.3665, the area associated with the z of minus 1.11. That gives us a net area effectively, or area between these two z values, of 0.086. So that's the shaded area on our diagram. Step 4 is the probability calculation. So for a batch of 3,000 bottles, the number of bottles containing between 750 and 751 milliliters is simply 3,000 times our probability, which is 0.086. So 258 bottles. In other words, of a batch of 3,000 bottles, we would estimate 258 of them lie between a contents of 750 and 751 milliliters, assuming our batch is normally distributed. I'll leave you with some tutorial questions to review in your own time. The answers are given on the right hand side in brackets. Further questions for you to review, and again the answers are given on the right hand side in brackets. Here's the bibliography used to help develop the presentation. Some excellent reference sources here. I would encourage you to review them for further information. I hope this has been of help to you. Thank you for viewing.